Hello and welcome to the last part of the evaluation of the triple lock, or essentially how to decode Unreal Engine packets, at least for Unreal Engine 4.2. I'm not quite sure which one it was. Anyway, the question was mostly how do I get from having a debugger like this to run the game to something like this. Let me show this. A few versions after the current engine version we are using here, they introduced the network analyzer, and it has some pretty nice views for us to explain what I'm trying to do here and why all this work in the previous videos was necessary. So as you can see, it shows packets that are sent over network, and that's what I want to decode and essentially recreate in the server. Each of these packets is usually made of sub-data, sub-packets. They are called bunches in Unreal terms, and they contain stuff, lots of stuff. Setup, initialized values for the properties, saying please spawn this here and there. And usually, most of the time, it's just updates. Player is now at position so and so. And yeah, it's pretty nested, so it's a lot of buffer in a buffer in a buffer in a buffer until I have my packet. And if I just look at this stuff raw in Wireshark, that's how it looks like. I have like one big blob of data where everything is inside that I would usually see in here. Like, could be like 3 or 4 of these packets in one. Because Unreal Engine tries to create something like a reliable connection over an unreliable connection, which is UDP. And so, in my example, PUBG Lite, for I don't know how long I can think now. Is it actually running? How do I even get network packets? So for this game, it's possible to run the game either as host or as client, and so you have the server or the client running locally while also being able to play with it. So I want to make this a server. Okay, confirm. Giga, go for it. Yeah, we did some pre-work here that this is possible. Okay, hello, welcome to the map. Blah, blah, blah. So let's take another instance. Yeah, I need to use Alt and Tab here. Binaries. So right now there is no networking going on. And if I run a second instance, I can join that first instance and then traffic would start. With a little pre-work, one can find a lot of the functions back from the original source code, because you can just check it out and have the right version that the game has. So it's easier to look up and then see if something differs. So you know how to modify your network code so that it fits the one from whatever game you have. Mostly interesting here are the serialize and bitwriter functions. I already have breakpoints on them in a regular debugger like this. And it's serialize bytes, serialize bits, write a bit, write int wrap, and finally send to. The idea is every time send to is called, one UDP packet is sent over the network. So if that happens, we can look at the stack and look back which functions were involved in calling that packet, and we get back to the main packet handling. For the other breakpoints, I can log out what data was sent actually. So let's take one of these breakpoints, for example, say editable. Break condition is 0. It just never breaks, it's just for logging stuff out, which will be a lot. I just make a little text, oh, that's this function which is called from here, which actually irrelevant for now, but later on that. The buffer address, which is used here, this will be useful later, and the actual data that was written there. So we will see all the function calls that actually write something to a buffer, which will eventually lead to a packet that will be sent. We also have a command condition, which is print stack. This is a function from x64 debugger that just when this is called prints the stack out. Let's see how that works. Hopefully my PC isn't freezing. So let me try to join. In the meantime, let's open the log so we see what happens here. And clear this out. So we don't even need much traffic for this. And we are joining. So now the server part is sending packets. Yeah, probably too long open that something crashed here. That is fine. Yeah, go bye bye. The other one, I don't know what happened here, probably also crashed, but I don't want to stop it yet. Actually I can, it doesn't really matter. Because we're just interested in the log, which is huge now. Come on. Okay, let's go back and let's have a look at it from the start. Obviously this is printing out a lot. And for every call to one of these functions, we get the call stack. That means all of these functions were involved in calling this particular function to write this particular bit into that buffer, and it has that bit. So we can go back and see who created that. Obviously all of these addresses here don't really help us much. Ideally we want to have the actual address inside the exe file to see where we're at. Like say I have this address somewhere, I can go there, I'm somewhere here in the assembly, and then I decompile it, I'm here in this function. If I look it up, I already have this function reverse engineered. That's what we did the last two videos, essentially, to find all the involved functions and look them up in the original source code. See if I have a bookmark there. You actor channel. Yeah. Okay. And yeah. Serialized in, write and wrap, where we at. Let's go again to that address. It's at the very end with 4 serialized bits. Serialized bits, serialized in packed. So there we have it, and that's the call where we came back from here. Just as an example for one of these calls. So it would be nice to have that address. Instead what we get, because the debugger doesn't know all of these addresses, is some symbol that it knows plus some offset. So we can look up each of these symbols and see it's usually something exported from the exe file, what its address is, and just add the offset onto it, which gives us the actual address inside the exe file. So to make this easier, I created a tool to do that. So right now we have a list of call stacks. So not just one call stack, but the whole list of call stacks. Let me load one. Oh yeah, also because I know every packet is essentially cut off by a send to call, I can just group all of these call stacks and cut off between every send to call, so I can just cut them into each packet. And in turn, because I know I'm on the server side, I can then just look up, that's packet number 9 that I'm currently looking at. So I can open the call stacks for packet number 9. Ta-da, that's how they look. And I already did some pre-work to write down which number it is of the calls, just the function name. It's essentially the output from the log, but only the top part. So if we go back, that's essentially just this line. So the actual values that we are interested in, we can see for each of them the actual address. These are decoded already. For this I just had to give it a list of symbol hints. That's essentially, these are the exports I was talking about, where I say, yeah, this is the address plus some offset. That's the address where the call stack would have returned to. Then I also, in the last 2 videos, or semi did that too, found all of the function names and wrote down where their address starts, where it ends, and so we can make ourselves already hints which function called which, to finally call the function that wrote a bit into the buffer. Alright, so we can also see that in one buffer a lot of calls and a lot of writes are done. So every time the address for the buffer changes, this is a new buffer where something new gets written into. So essentially this is all the writes that were necessary to create this packet. Everything that's in here, all these bytes here, and on a higher level something like this. These buffers and buffers, that's what we are looking at here. And also, just from a logical standpoint, when we have a big buffer and then write it into another one, like here for example, where something was created first and then we write it into another one, that these can only happen if the thing we want to write into the buffer had been created before. So all the calls before, somewhere in here, is all the information we need to know what this data actually is. So we can start from the outside essentially and unpack the packets in this case, or actually bunches. They are still labeled wrong in my dissector code here in Wireshark. But this is essentially the goal, that we can write code for Wiresharks that can show us all the data that's in these packets, and then also decode the payload that we are currently interested in. So one of these packets is called one bunch, and there are 1, 2, 3, 4, 5 in here. It's one of the big packets. It's the first packet the server sends to tell the client, hey, please spawn a player object at this part of the map. And this is a bit stream, so we don't necessarily see, for example, this value where it would appear in here, because it could be bit shifted and only by chance 1 in 8 be at the right byte position that I could compare the data. So bit streams are a little bit tricky, but we know what has to result in it, and we also know how many bits are needed for that. So we could, for example, use a tool like BitCutter, which I wrote to cut bit streams, to now take the data and take it apart. So I already did that. That's is pre-done work here. This took a little bit, but just so you can see the result of the whole idea. So I give it a bunch of data that I copied from the network. This is a payload. I already know this and how this has been read from the data here. So I just know these are 3D9 bits of data. This is not divisible by 8, so there will be left data at the end. And I have this all in here. And here the upper bits are empty, so they are left over. I read from it, for example, 1 bit, 32 bits. Then there are reads where it's reading consecutive bytes, depending if the highest bit is set. So this is a compressed int, essentially. And I may read a string, for example, where it first has 4 bytes for the length of the string and then the actual characters for the string. And if I run this, it actually shows me then how many bits it actually used up, for example, for the variable length ones, and the actual value that was read there. So I can decode the data one by one and see if the data that I'm expecting is in here. As you can see, it's pretty successful, as I can see valid strings, which I would have not seen before in the data. And I also use up exactly as many bits as I am expecting to use up. Let's see here, number of bits of this payload is exactly the same. So how was this possible? Obviously I would expect to see the data here. Let's see on the right. Somewhere in here, sooner or later. Let's find something like that. For example, we should find the call that writes these 3D9 bits into the final packet. Let's see if I can find that quickly. I should write a little search function here for stuff like that. I haven't yet. 3D9, there it is. So here we have essentially it writing the header for this. You can see it's channel type 2, that's the 2 from here. True and false, that are these two values. Then 27F, here we are at the right place. We can also say we came there via getting this way. And so we can already see that the value that is the data that was written into here is the data we are expecting. Okay, so take this apart. So if we look further up, we need something that starts with O2 into its buffer. And I'm not sure which one it was right now. Let's say this one. It writes a bit, and then it writes some bytes. It could be possible, but the value would be wrong. The next byte would be a 0, 1. But so this is a lot of puzzling. We also have the strings I can see here. Let me copy that, for example. Hello notepad, give me data. What the fuck? Yeah, 2F is how it starts, right? Okay. Let's now look at this in the hex editor. And there's our string from the packet. Where was it? Yeah. Game, blueprints, PC Lite. So we know which object we're actually replicating here. This is a setup packet. For other reasons, we know for this channel, which will send updates for this particular actor. This is the first packet we ever received. All the ones before have something else in them. And so on. We know this is the initial packet, this is setup data, and next we know what we are setting up here. So internally the game now knows from the assets which object to load, and then we fill out its properties. But to get to that, we still have to first figure out how to cut down our data, what comes after what, so we can later write code that can read this in the order that it was created. It's still not quite clear what the higher order is of this stuff, even if I already indented it a little bit. To make more sense of this data, and then later go into our server side, which is a dedicated server, not a local gamer, not a local game instance, to have the same data. The reason for that is just LAN, L-A-N. Traffic is unencrypted. You could just override a specific bit to make it for any other game as well. And it's supposed to also have a client that runs, and it's supposed to run in a very fast network. This isn't made for working over the internet. It could potentially, but very badly. Instead, a dedicated server is not running all the graphics part, just maybe the physics part, and it's loading only specific parts of the server. Its main job is just to exchange all the updates between the players where everybody is and tells it everybody else. So that is way more efficient if a dedicated server does it, so that's why we're writing one. And we can just now go onto the server side and look at our code to adapt it to create the same packets, and finally the game and our server can talk to each other. Yay, and we also know what stuff we need in the packets. So let me give a little preview. There are still steps that I'm not having explained yet how we got so far, but just for example here, for this object we serialize if we want to send the location, rotation and scale. With the initial packet we won't. We also give it a unique ID for the network. It has an object ID but also gets a network ID in case it gets instanced multiple times. This, for example, is a thing that is not coming in the original source code. It's something we have to add later, where we can see, oh, this is missing in our code. If we add this, it finally matches with the game, and that we can talk to each other without crashing. And more stuff. And interestingly is replicate properties part of this packet, because the calls to which property gets essentially serialized next is defined in the class object of that player object, which is in the assets, which is also compiled in the source code of the game, which is custom to every game. Now we first off see every type of object property, sorry, which the type is of the property that we're serializing and its value. And we also can go into the assets and finally match this to the properties that are in the files. Let's see if I can show that right quickly. Release. I still have to update this tool. It has still a bug, so I can't show all the properties. Let's go back to the first packet. First bunch, I'm sorry, I'm still confusing this terminology. And let's have a look at this path here. So this is an asset path that's inside the asset files. So I loaded all the pack files. And content is essentially what's in here, the game folder. So we go game. I should have sorted this. Okay, let's try that again. Okay, content. So we are looking for blueprints. Core, in this case PC Lite. I should probably make this bigger here. And we're looking ST extra player asset. Okay, and in here we will find an object called default blueprint ST extra player controller PC class, which has quite a lot of objects, properties. Which gets set in the second packet here. Compare that. So all these properties, even if you don't know the name now yet, we can still figure out that a byte or an object or an enum property is this or that. There's also the common possibility of creating an SDK for Unreal Engine games. It's very often used for cheat makers, but in this case these SDKs also print out the flag for these properties, and in these flags there is a flag if it's getting replicated or not. So we can figure out we can already filter out all the properties that will never get replicated anyway, and then also we can when we do these debuggings here, we know the functions that are responsible for serializing an object, make breakpoints there and log out what the object name was. So that is possible with a little bit of extra work. Well, maybe not with a breakpoint, this would be a TUT function with an SDK or so, but you can definitely log out in what order what property comes here. So that is a great hint for creating the same structure on the server side later. So, but still, how do I get, without just guessing, or maybe getting more information, out to all the bits and the matching values that I have in here. So figuring out all these values in here. At the beginning you don't know what comes next, so you have to guess, is it this buffer, is it this buffer, and you just try to decode it. But as I said, it can only be a buffer you had before, and it can only be a buffer you haven't visited yet. So just go by the addresses, and that already helps a ton. But let's do a magic trick, and for that I first want to edit a file to show how that works. Let me open one of these packets. Nope. No, packet was right, never mind. Packet 9 for example. And let's take only two or three stacks. This was called, then something else was called. Okay, whatever. Let's cut all of this off. We only have 2 stack frames in here. Let's save that as test. Test is always a good name if you don't know what to do. Let's load that. Okay, so we only have this call stack and this call stack. Both already decoded, all the functions. How about this? So I can obviously make one call stack into a tree that is just one node after each other. So I just add one path, one of these call stacks, and then I try to append the next call stack, but if the return address is the same as the previous one, I make it a node of that. So you can see these both calls to serialized bytes and again serialized bytes come from this function, and this function is first writing at this address. Let's actually go there. I can copy this and go to IDA and see what it's doing there. Oh, yeah. Clicking and double clicking, 2 functions I implemented here, sorry. Serialize object was called, and we are in this part of serialize new actor. At this part, I think this is the handle of the object that it's writing here. And at this part, we are down here. I haven't commented what it's actually writing here, but we could look it up in the source code. So you can see, you can have a higher level view of how the packet is created. So this function calls a few times this function, which in turn adds this, that, and that buffer, and then match back to the actual log to see, okay, this must be of the buffer that I'm writing next in my bit cutter. It's a little bit tricky, but taking all of this together, you can make very high level view of the whole thing. Let me show how that works if you have a full packet. Where was it? Number 9. So we load quite a lot calls, so 417 decimal. Okay, let's make a call tree of that. This is very long, yeah, and not very useful yet, but let's unfold to level 2. Okay, now this makes a little bit more sense in what order stuff was done here. So we first call replicate actor, which comes from internal process remote function. Yeah, so some event called the function, the remote function, to spawn that actor. And now that function has to handle that call and make a response. It calls replicate actor, which creates all our initial stuff that we've seen in the first packet that I've dissected here. Then we set the properties for the call, which we've also have seen all of these, all the properties. Let's keep this next to this. And then after we created these buffers, we append a header and a header and the payload. And finally we send these 3. So essentially all of this up here is creating the first 3 bunches. No, it's creating the first bunch. Right, this, okay. This is a function that is appending one of these packets to the list here. So one send bunch is sending one of these. And it itself also appends stuff to the buffers that we've created before, and that are the exported bunches and the must mapped GUIDs. I don't know how to spell this. And then everything is set together to make the rest of the packet header here that we have in before. And finally appends the buffer we created before. So isn't that nice? And we see all this in 3-4 nodes. That's all it's doing until here. Then here comes another field header content, and we send another bunch. Then we send more properties. I think then because it was sent, so for a higher level view, the first thing it sends is that we are in this object from the assets, this thing, which itself is made out of other things. It has component attached to it. So I'm not sure if it was number 3 or number 4. Yeah. No. I have not even got so far. I haven't even gotten so far. Okay, not so bad. I can refine that. I just need one of these big buffers where now it's writing ASCII. I can already see it from the hex. Nope. Give me that data. What are you? This is BP Lite PC Survive HUT. So that is everything your UI is doing, the overlay. I can also find that object in the files. So that would be somewhere totally else. Light PC blueprints game and the hood asset, and it has, I can always use a default object here which doesn't have much properties. Well, I'm not sure about that because the generated class can attach a lot of stuff here, but I'm pretty sure I could see it in the data here what it is. Let's take this BP Lite Survive HUT C without the default. Interesting. Okay. Just one above it. Okay. Yeah, which has a construction script and stuff attached anyway. So it works the same as with first player object. It's attaching all the properties for that. So that's what we can see here in the call tree. And yeah, so the idea of just imagine one call stack as one path in this tree and just adding them all over each other, you can make higher level what should I say, higher level remarks about how everything works, make a picture of it, and then finally match it to, oh yeah, this could be this, and this, because essentially, okay, essentially we have, I don't know, maybe the first initial stuff for the player object itself, then the first stuff for its first component, that is a HUT, then there's another component, and so on, and so we can decode all of these packets, and later also write code that, like, this is folded here, fold this data as well with all the sub data in it, so we can view any packet like this. And also again later fix our server side to accept the same properties and expect the same stuff to spawn a player on the actual game. And obviously I can do all the same stuff on the source side, on the server side, where I can make any log I want to. Um, this version of PUBG Lite obviously has an engine version before that was introduced, so I would have to port that in to have it in my server instance. But yeah, with just the logs you can do the same thing. I have an option here that does the same for our own logs. And yeah, and then finally we can recreate these packets that are needed for the game to start and to exchange its updates. Essentially what will be happening next is, after some setup stuff, there are a lot of smaller packets that just do updates of where I am now and what position and how I'm rotated, and they will just repeat over and over. I'm not sure if they have an example here in their preview where you can filter out, yeah, this function. So these are, for example, maybe just setup packets. Whenever, for example, new actor is spawned, every time you shoot a bullet or something. And in between are plenty of small updates that just say player is here, player is here, player is there, and so on. So yeah, with Calltrees you can have all of these packets back and recreate them. And this should work not only for my game, but pretty much any other Unreal game. If you got this far into the video, thank you for listening. I hope this was interesting and helpful to other people as well. And yeah, see you soon. Have a nice day. Bye.